Hello and welcome to the lecture series on power converters or power electronics 2. This is the second part of lecture on buck converter, and let us try to quickly recapitulate what we studied in the previous lecture. In the previous lecture we saw that we can develop the circuit of a buck converter like this. This is the input DC power supply, and we have the switch, the diode, inductor and capacitor to smoothen out the voltage ripple that will otherwise appear at the output. And we tried to write down the equations governing the circuit. There were two modes of operation. In mode 1, these are the equations wherein the inductor voltage is related to the input and output voltage by this relation, while the rate of change of the inductor current was V in minus V naught by L. Here let me tell you that there are few assumptions that we had made in the previous analysis of the buck converter, and we will continue with those assumptions. What were those assumptions? The assumptions were that we were confining ourselves to the steady state analysis of the circuit. Second, we are assuming that the capacitance that is connected to the load is large enough to ensure that the output voltage is almost constant. And the third assumption is that all the components of this power converter circuit has been assumed to be ideal. That means there is no drop through any of these switches. This is a fully controlled switch. It could be an IGBT or MOSFET or BJT, and this is a diode. We are assuming that there is no loss associated with these switches during conduction and turn on and turn off periods. So with this assumption, let us move forward. So the second mode was when the interval between dt and t where the switch has been turned off. So in that case the diode will start conducting, and we have the following equations. The inductor voltage, since the diode is now conducting, will be equal to the negative of the output voltage, and we know that the inductor voltage is related to the current by this expression L di by dt. So this is equals to minus V naught, and consequently we have got a relation of rate of change of the inductor current, and which is equal to minus V naught by L. And since we are assuming that the output voltage is almost constant, that means this dIL by dt value is a constant. So that means in the case when the switch is on in mode 1, the current through the inductor is linearly increasing, because V in minus V naught upon L is a positive quantity. Why it is a positive quantity? Because V naught, which is the output voltage, will always be less than the input voltage V in. So V in minus V naught will be a positive quantity, and divided by L will give you a positive constant quantity. That means dIL by dt is a constant value indicating IL is linearly increasing, while in the second case when switch is off, IL is linearly decreasing. From these two relations we also found out the relation between the input and the output voltage, and the gain, which is given by V naught by V in, is equal to the duty ratio D. So that means since the value of D varies from 0 to 1, so that means the output voltage VO will vary from 0 to V in. And please remember that right now we are considering the continuous conduction mode. So I have written this equation keeping in mind that I have got a continuous current flowing through the inductor. So this is the case that we are assuming in this lecture. We will take up the discontinuous conduction case also in another lecture. So let us now try to plot the various waveforms that will appear across the various waveforms that will be appearing in the buck converter circuit. So I had drawn this type of the axis. Okay, on the y-axis I have got these quantities, Vg, which is basically the gate voltage. If I am considering a MOSFET, we are required to provide a gate voltage to the MOSFET, sufficient gate voltage to the MOSFET to turn it on. Similarly, I will try to plot the voltage that will be appearing across the inductor in one complete cycle. Similarly, the current that will be flowing through the inductor, the current flowing through the capacitor, the voltage across the capacitor, which is also equal to the voltage across the load. Similarly, I would also be plotting the waveform that will be appearing across the switch, the voltage across the switch as well as the current that will be flowing through the switch. Similarly, I will be plotting the waveforms of Vd and Id, which is the voltage across the diode and the current that will be flowing through the diode. So in power electronics, please remember that these waveforms are of quite importance, because based on these waveforms and their values, we basically design a power converter. So let us try to see the various waveforms that appears in a buck converter. So let us start by giving a voltage signal to this buck converter. So as soon as we provide the voltage signal, this MOSFET will start conducting. So if it starts conducting, I will have this type of circuit. So that means this positive polarity appears across the cathode of the diode. That means this diode is open circuit. So no current is flowing through the diode. So it is as good as this diode is open circuited. Okay, so let us try to plot VL. So for plotting VL, we can see we have already obtained an expression of VL in mode 1 as well as in mode 2. So from mode 1 we have VL equals to V in minus V naught, and since I told you that V in is greater than V naught, so this will be a positive constant value. So let me try to plot it here. So this is V in minus VO. Okay, what will happen in the case when the switch is turned off? Okay, let me take the case of mode 2 afterwards. First we try to plot all the waveforms in mode 1. Okay, so in mode 1 the current IL, so dIL by dt equals to this value. That means this is a linearly increasing current, and also we are assuming that the current is in continuous conduction mode. That means it will be starting from a finite value, and it will be after completing one cycle coming back to that finite value, and the process will go on. So let me try to plot it here. So it starts from some value, and let me call it I minimum, and it reaches a value of I maximum. So this is I maximum, this is I max. So let me write down here itself I max, and this slope is V in minus V naught by L. So this slope is V in minus VO by L. Let us now try to see what would be the current that would be flowing through IC, that is the capacitor, which is connected in parallel to the load. So I have wrote here the equation for IC. So IC, the current, this is IC which is coming into the capacitor is equal to the inductor current minus the output current. So simply applying KC here at this point, we obtain this relation between IC, IL and I naught, and I naught we know is equal to the voltage that is appearing across the load, which is V naught divided by R. So I have written I naught as V naught by R, which is again a constant value. So that means IC is IL minus V naught by R. So this was IL, so IC would be this minus V naught by R. So let's say that we obtain this type of waveform. Okay, the slope of this current would be same as the inductor current, only the difference would be that it would be starting from this point, which is basically I minimum minus V naught by R. Okay, and it would be reaching this value, which would again be I maximum minus V naught by R. Now let us try to plot output voltage, which is also equal to the capacitor voltage. Okay, so although we are assuming that the output voltage is almost constant, it is almost constant, and I can just simply draw a straight line here showing the output voltage to be constant. And now let us a bit precise and let us try to see how exactly will the output voltage look like. Okay, so for the time being, let me assume that there is a slight variation in the output voltage. Okay, but that variation is very small, and let us see how that variation would be there. So to see how the output voltage, which is equal to the capacitor voltage, will vary, let me write down one relation here. We know that the charge which is accumulated in the capacitor is given by C times the voltage appearing across the capacitor Vc. So if I try to differentiate it, so dq by dt equals to C times dVc by dt, and this is nothing but the current through the capacitor. So IC is C dVc times dt. Okay, so if I am assuming that Vc is a constant, then this term will vanish. Consequently, IC will become equal to 0. Okay, that means there is no flow of current to the capacitor or through the capacitor, throughout the capacitor, when the output voltage is ideally constant. But let us assume that it is not constant but close to constant. So how that waveform will look like? So you see this IC is basically dVc by dt. Okay, so that means whatever is the waveform of IC, its derivative is IC. Okay, so whatever is the waveform of IC, its derivative is IC, and we can see here that IC is linearly increasing here. So basically it is an integration of IC. Vc will be an integration of IC. So integrating a linearly increasing a waveform would result in a quadratic form of equation. Okay, so it would somewhat like this. So increasing in a quadratic fashion, like your quadratic equation. Okay, so this Vc would basically be a function, it will be proportional to some t square. Okay, the time square. And in the case when okay, let me talk about this case afterwards. This will be the variation for the period from 0 to t. Now let us come to this Vs and Is, the voltage across the switch and the current that would be flowing through the switch. So when this switch is conducting, so the voltage across this would be 0. So let me try to draw it. It would be 0 here. What about the current? The current Is is nothing but the current IL which is flowing through the inductor. So this Is, let me draw it with a different color. Is would be same as this IL. This is your IL. So it would be same as your IL increasing. So this is Is, while this one is your Vs. Okay. Now come to Vd. Vd is the voltage that is appearing across the diode. So in this case, since diode is not conducting, it is not conducting, so we can find it out. So Vd is the voltage across diode, and this is nothing but if I apply KVL in this loop, okay, so this Vd will become equal to minus of Vin. So Vd will be minus of Vin. This is minus of Vin. Okay. What about Id? So in the case when diode is not conducting, Id will be equal to 0. So Id is 0 here. Okay. So this was mode 1 from 0 to time dt. This was mode 1. Sorry, let me write it here. This is mode 1 from 0 to dt time. Now let's move to the second mode, which starts from dt and ends at t. So in this case, let's start with the gate signal. Definitely we don't have to provide any gate signal to the MOSFET to turn it off, and in that case the switch will be as good as your open circuit, and this now diode would be conducting. Okay. So let's start with drawing VL. You could see here that the voltage that appears across the inductor VL is related to the output voltage and equals to minus of the output voltage. So this will become minus of V0. So this is minus of V0. Okay. So this is your VL voltage, and after that it will continue as in 0 to t period. Okay. What about IL? We can again see here that IL is a linearly decreasing current, because minus V0 by L is a constant quantity and negative quantity. So dIL by dt will be a linearly decreasing current. So it started from I max and it will again reduce down to I minimum, and then again it will rise. Okay. And this is the case when the current through the inductor is continuous in nature. Let's take now IC. IC, I had told you that equals to IR minus IL minus V0 by R. This relation will hold good in the second mode also. You could see here we can apply KCL in this mode also, and you will get the same expression. So IL minus V0 by R. So it would look somewhat like this. Okay. So I mean minus V0 by R will be this value, and then again it will increase. So this is IC, the current through the capacitor. Now come to the output voltage. So here we have this relation. So you could see here again, if I integrate the current through the capacitor, I can get the variation of the voltage through the capacitor. So integrating this linearly decreasing curve is basically again a quadratic equation, but it would be negative now. So something like this. Okay. And then again it would be increasing. So waveform is like this, and depending on the value of C, this variation, this is your delta V naught. We will obtain the expression for delta V naught also equal to delta Vc. So as the value of C increases, this variation delta Vc will reduce further. Okay, and for the purpose of analysis, we have assumed that to be almost constant. So next we have got Vs. Now this switch is not conducting and it is open circuit. So now this voltage will be equal to minus of Vin. So this value is minus Vin. So this is your voltage across the switch. This is also called the stress on the switch, and this is a very important parameter in determining the selection of the switch for a particular converter and for a particular application. Okay, so the lower the stress on the switch, the better is the converter, because it will lead to a converter in which you require lesser rating of the device, and consequently lower cost and lesser loss. So these are the various features in a converter wherein the voltage stress is very less. Okay, fine. Now let us see what is IS, the current that is flowing through the switch. Now since switch has turned off, so the current will also reduce to 0. So it has reduced to 0, and again it will increase and it will go like that. So this is IS, the current flowing through the switch. Now come to VD, the voltage across the diode. Earlier in mode it was minus Vin, now it becomes equal to 0 because diode is now conducting. And the current through the diode is same as the inductor current. So inductor current is this, so it would be like this. Okay, so it starts from I max and reduces to I min, and then go to 0, and then it remains 0 for the next mode of full cycle. Okay, so these are the various waveforms that are associated with a buck converter. Now we will focus our attention on finding out how the capacitor C and how the inductor L are basically related to the ripples in the voltage and ripple in the current respectively. Okay, and this is an important part of buck converter, wherein we can use this relation between C and delta V and L and delta IL to find to design the converter. Okay, so let us see how we can find out. So let me erase which part. So let me erase this, and I will try to solve it here. Okay, so I am basically interested in first I will try to find out the current ripple, and the current ripple is delta I L, which is I max minus I min. Okay, so you know that the current through the inductor varies from I min to I max. Okay, and this difference is the delta I L. Okay. So first of all, let us try to find out the average value of the inductor current, IL. Capital IL is the average value of the inductor current, and this is equal to integration of this IL dt from 0 to complete cycle. This is t time and this is your dt time. So integration from 0 to t, and this divided by t. So this will be equal to, now integration of IL is basically the area under this curve. Okay, so let me draw it. So average value of IL is basically this area, isn't it? Because this integration is this area. So we have to find out the area of this curve. We can easily find it because this composes of this rectangle and a triangle, and I can easily write down the area of this rectangle, which is I min times t plus the area of the triangle, half the height, which is delta IL, into, so let me write like this, plus half of delta IL into this time t, and divided by t. So t gets cancelled, and finally I have this I min plus half of delta IL. So this is IL. Okay. What about I max? So I min equals to IL minus half of delta IL. What about I max? I max, you could see here this I max is basically this I min plus delta IL. So I min plus delta IL. So this would give me IL plus, if I put it here, I get half of delta IL. So this is I min and I max expression. Okay. Again, I can write down in place of this delta IL, you could see here, just see here, dIL by dt equals to minus V naught by L, and this is equals to delta IL by 1 minus d into t. I can write the value of delta IL from here. Okay, or I can write from here. I can use any of the expression. So if I put it there, then I will get I max is equal to IL minus, this is minus, this becomes minus of half of V naught by L times 1 minus d into t. Okay. Now from here, from this expression, I can find out what is L. Okay. So you could see here, I am talking about continuous conduction mode. So in continuous conduction mode, this I max, okay, or let me try to find out I min, because I am interested in finding out L. So for that I will try to find out the minimum value of inductance which will ensure that there is a continuous conduction through the inductor. So I have to find out I min. Okay, so let me just erase the things here. So I min is equal to IL minus half of delta IL. Okay. Okay, so this is equal to IL, then it becomes, if I put from here, I get plus half V naught by L and 1 minus D into T. Okay, so this has to be greater than equal to 0. I mean has to be greater than equal to 0. Now what about this IL? Can I write down this IL in any other form? Yes, I can. So you could see here that I small I L is equal to small I C plus I naught. Okay, for any instant. And let me try to find out the average values now. Okay, so average value of IL is IL and average value of IC will be equal to 0 because of the principle that we discussed, and that is capacitor charge balancing. Okay, I talked about volt second balance in inductor and capacitor charge balance. Okay, so if I apply that principle, the average value of the capacitor current will be equal to 0, and plus this, since this is a constant value, and this is equals to V naught by R. So that means IL is V naught by R. I put it here, and finally if I put it here and rearrange the expression and represent it in terms of L, then L minimum will be equal to 1 minus D times R upon 2F, or I can write it in another form, which is V naught into 1 minus D